In this video, we'll discuss polar derivatives and then polar integrals. So let's start with derivatives. We know from parametric derivatives that we have dy dx. Parametric derivatives, a couple lessons back, said that dy dx is equal to dy dt over dx dt. Here we'll make it dy d theta over dx d theta. And so what we have to do, if you look at our graph here, we have to figure out what a slope would be. So we're looking for kind of a tangent line here, like this red line. But for example, the slope that I just drew there is 0. And that's the change in y over the change in x. So we're looking, again, the slope that we need is dy dx. So this is the x-axis and the y-axis, even though we have a polar equation where r is defined in terms of theta. So important to remember, first of all, we're looking for dy dx. Second thing to recall is that y was r sine theta and x was r cosine theta. You can go back a couple lessons back and you can see, I think last lesson, and see where this information comes from. So if we're taking the derivative of y with respect to theta, one thing we have to recall is that r is a function of theta. You can see it right here. R is the function 1 plus sine theta. So anywhere there's an r, we have to take the derivative of that with respect to theta. So we take the derivative of y with respect to theta. That'll be dr d theta. We're applying the product rule. So the derivative of r is dr d theta because it's some different function of theta every time, times the sine function, plus now the derivative of the sine function is cosine. So we did derivative of first times second plus the derivative of the second times the first. And I'm going to repeat the process in the denominator for x. So dr d theta, cosine theta, and now we'll have r, because that's the first, and the derivative of cosine is negative sine. So it would be plus, but I've made it negative based on the derivative of cosine being negative sine. So this will be our guide for the first derivative. So we're going to apply that to our the curve we've been working on, r equals 1 plus sine theta. So let's use this derivative to find places where or angles where the slope of the tangent is 0, also known as horizontal. The tangent line is horizontal, or the tangent line is vertical. So it should be somewhere over here. Our horizontal places should be already one is marked, and then there's one down here and one down here. So we're looking for those locations. So for this particular function, dy dx is dr d theta. So we're here, dr d theta. We have to look at this and take the derivative with respect to theta, which will be cosine. And then I just recopied sine. And now it's plus r, but r is the whole function, 1 plus sine. And then I'm recopying cosine. All of that goes over dr d theta we already took, but again it's cosine, times another cosine, minus the r value, times sine. So we have to fill in 4 things. We have to fill in dr d theta, and r. But sine, cos, sine, those remain. So we have this, and now if we're trying to find the horizontals, so horizontal will be when the top equals 0, and we can factor out a cosine from the top. So we'll have cosine times sine plus 1 plus sine. So I just factored cosine out of these two, and we're going to set that equal to 0. I'm writing setting it equal to 0 because that'll give us the horizontal tangent lines. So we can solve this. This will be cosine equals 0, and cosine equals 0 at pi over 2 and at 3 pi over 2. So pi over 2, that one's a valid solution. 3 pi over 2, we're going to find something that's wrong with it. So for right now, I'll just tell you that we're going to reject it. We'll see what's going on with 3 pi over 2 in a second. And then over here you'll have 2 sine plus 1 is 0. And that means that sine is negative a half. And that happens at 7 pi over 6 and 11 pi over 6. Actually, both of those are keepers. Those are both valid solutions. If you don't believe it, you can look right here to see them. I'll highlight them in red. We've got, that's 11 pi over 6 and 7 pi over 6. Those are the horizontal tangents. Now 3 pi over 2, that's where the object closes back in on itself. So it's kind of this cusp that's in the center of the image, and that doesn't have a defined derivative. And we'll see that as we work for the vertical tangent lines. So I just wrote vert there for vertical tangent lines, and I'm going to, this time it'll be cosine squared minus sine theta minus sine squared theta. So I just distributed. Now these all have sines in it and this doesn't, so just a little bit of trigonometry. That's 1 minus sine squared minus sine squared. Oh, I'm sorry, I never set it equal to 0. And if you do the solution here, you'll find pi over 6 and 5 pi over 6. So from here you can just take this quadratic in sine and factor it and solve. Just for the sake of brevity, I'm going to leave that to you. Again, that's at pi over 6 and 5 pi over 6. But there's also another place where that equals 0, and that other place will be 3 pi over 2. And it's 0 there because, again, we're going to reject it because it's not defined. It's at this cusp. So we have to make sure that any of the values that we find aren't false positives. So we have these two values. So I'll just get rid of these 3 pi over 2's. These two values, again, I'll highlight these in red. It's about here. My image isn't perfect, but it's pretty good. Those are the two vertical tangent lines. So that about does it for derivatives. So just to recap for polar derivatives, we started with dy dx because that's always our motivator. We're looking for a slope of a tangent line to a curve, and that's still going to be rise over run. So it doesn't matter that we're in polar, we're still looking for rise over run. So we do dy d theta over dx d theta. We use these two equations and then do the derivatives all implicitly with respect to theta. And we've got the derivative here. We applied it and found horizontal and vertical. So that's that. Okay, now we're going to move on from there to integrals. So for polar integrals, I'll do it right here. We'll use the same image as just a basis, just as a case study. For a polar integral, let me get rid of the tangent lines. Okay, a polar integral, you can see this would be quite problematic if we just tried to use rectangles or if we integrated dx. Because our rectangles would be built with a height here, and that would be measuring this function against itself. It would be kind of like the top part of this function minus the bottom part of this function so that you could get your integral dx. Or think about slicing this with little rectangles. The heights of those rectangles are not easily obtained. And if you'll recall, this thing, if we tried to convert out of polar and into rectangular, gave us a very complicated expression. The polar solution to these kinds of curves to find the integral is rather than fitting vertical bars, we actually fit sectors. Now keep in mind that the image in blue is not a perfect circle. So what I'm trying to highlight here is I'm trying to make this red piece, the crust of the pizza slice here, I'm trying to make that a member of a perfect circle that goes about the origin here. And I know there's a little bit of hang off there, but just so imagine that we've got dozens or infinitely many of these slices, all of them having this little bit of extra hanging off. But if we were to add up the area of all those and make them infinitesimally thin slices of pizza, then we'll get an area. And you can see this even happens on this smaller part of the graph on the bottom. These little slices of pizza, eventually, if we do enough very thin slices and calculate the areas, we're going to get the area enclosed by this object. So the question really is, what's the area of a sector? And from previous coursework, you should know that it's 1/2 r squared theta, where theta is measured in radians. We don't want the unit of degrees on it. So now polar integral, we will extend this concept that the area enclosed will be the integral of 1/2 r squared d theta. So remember, what the integral is good at is taking very thin pieces and adding up infinitely many of them. So 1/2 r squared, this d theta is to represent the infinitesimally thin slice of pizza. So you can see the tie between the area of a sector and the area of an infinitesimally thin sector. And then what do we integrate from and to? Well, it depends on the object. This object, when you go from 0 to 2 pi, closes itself up. So you'll have to figure out what those limits are. So for this object, if we wanted to, in the example, calculate the area, it's just the integral from 0 to 2 pi of 1/2. Now r squared, r is not just a simple expression, it's the 1 plus sign. So 1 plus sign, all of that expression squared, and then you integrate with respect to theta. This integral is not extremely easy. I'm not going to do it now because the focus here is how do you set a polar integral. If you want to do this, what you'll do is expand this thing out. You'll have one of the terms that's the hardest is going to be sine squared. And I will give you a little clue as to how to get through that. And you may recall this double angle identity from pre-calculus study. And it's cosine of 2 theta equals a few things, but the pertinent one here is that. No, not true. The pertinent one here is that. So if you encounter in your integrals here any cosine squareds, you can use the first one I wrote. If you encounter a sine squared, as we're going to here, you take cos 2 theta, and you're going to isolate the expression sine squared, and then that will give you something that's a bit easier to integrate. This thing will give you 3 terms, but only one of them's tough, and again, it's the sine squared term. Cos 2 theta has another representation, which is cos squared minus sine squared, but it won't be very useful in the context of AP Calculus. So, quick recap, we have derivatives and integrals. Derivatives are based on parametrics, dy d theta over dx d theta. We did implicit differentiation there. And then we wanted to find the area enclosed by this object, so we cut it up into infinitely many little thin slices of pizza, and we used 1/2 r squared theta to build an integral of 1/2 r squared d theta. Last comment would be if we wanted to take, say, that object, and then, I don't know, a circle like this one. If we wanted to find the area that is inside the circle but outside of the cardioid, what we would do is actually take the area inside the entire circle, but only starting from here. Let's call this angle alpha and that angle beta. So we'd integrate from alpha to beta, and you'll have to find where those are when they meet in a particular problem. And then you'll do the red curve, so you'll do like 1/2 r squared on the red curve, and then you'll subtract out 1/2 r squared on the blue curve. So that would be bringing little slices in here, whereas the red curve would go all the way out. And then we integrate that thing d theta. So in other words, you kind of do them separately and then you subtract the areas. But a key point is we're not including this area down here. And actually, we're only including the area from that line to that line. So it kind of ignores the bottom of the circle and only takes the portion that begins at angle alpha and ends at angle beta. So you'll do these two. I've color-coded them. This 1/2 r squared theta for r on the red curve, this half r squared theta for r on the blue curve. And that does it for polar derivatives and polar integrals.